Hi Stat students, this is the second example problem in the Chapter 22 lecture notes. So I'm going to run through this. I'm going to do most of this work on the calculator. That will save a little bit of time on the mechanics section. In this one, a company's been manufacturing batteries. They have a mean lifespan of 5 hours. New process has been purchased by the company. That new process is advertised to make batteries that last over 5 hours. And we'll convert to minutes here. Our data is in minutes. So 5 hours, 300 minutes. This would be battery life when in continuous use. In a test of 12 randomly chosen batteries that were manufactured with the new manufacturing process in place, the company measured the following lifespans in minutes. So we have 12 batteries. You should stop here and put those values into your calculator. I just put them into list 1. Is there evidence that the company has met its goal of lengthening the life of its batteries? We're going to use an alpha value of 0.025. So the parameter of interest here, actually, when it says is there evidence, that means hypothesis test is what we need. The parameter of interest is the mean life of batteries using the new process. What we have here is the hypothesized mean is 300 minutes. The mean with the new process is not increased. And I say not increased here because it was 5 hours originally before the new process. We want to know if we have lengthened the life of the batteries, so our alternate hypothesis is that the mean is greater than 300 minutes, that the new process lengthens the battery life. So hopefully this sample of 12 will give us evidence that we have lengthened the battery life. Now if you look at the data, we do have a few values that are less than 300 minutes, so I guess that would make us suspicious that the new process isn't doing what it's supposed to do. Alright, so our assumptions and conditions. The sample states that the batteries were randomly chosen. Thank you very much. The independence assumption, you could list it as an assumption here or not. I do on this one. The batteries operate independently of one another. 12 batteries is less than 10% of the population of all these batteries. And we need to look at the nearly normal condition. We need to see if our 12 batteries are normally distributed. So here's a histogram of batteries that were put together. Looks like here the width is the X scale value, or the width is set up as 20, and it starts at a value of 240. So 240 to 260, 280, 300, and so forth. So you can do this one on your calculator. I'm just going to use this one here. It is certainly unimodal. It is somewhat symmetric. It's not great symmetric. You can squint your eyes and maybe you can see some symmetry there, but it's not great, but it's okay. The idea here is that we do want to run the hypothesis test, so we're going to be a little lenient on this. We certainly wouldn't stop our work with this situation. When would you stop the work? Well, if there's like extreme outliers, or if there's an extreme skew in the problem. And we don't have that. This is the normal probability plot that we looked at in the last example. And this one, remember, you can do second stat plot. I've already got it set up from the last problem. I'm going to do zoom 9 just to get the new, zoom 9 to get the new version of that. And we're looking for this to be linear or approximately linear. It's a little more wobbly than the last one, I would say, but in the grand scheme of things, it's not awful. It doesn't have a large curve in it or anything like that. There's no, there's no really bad places where it varies too far from this, what you would eyeball as the linear portion. So we'll proceed. We'll go to the next page here. This note here is the same as in the last example. So just some word suggestions and some cautions against using the word normal. So we've met our conditions. We'll proceed to perform a one-sample t-test for the mean battery life. Our significance level is 0.025. All right, our sample statistics. The initial place you're going to get that is by running one variable stat. So stat calc one variable stats. And we get these values. So you can confirm that you get this with your data in your calculator. Sample size is 12, meaning degrees of freedom is 11. The t-test statistic, if you plug in these values into this form, you're going to get 0.909, and the p-value comes out to 0.191. Remember, in the coffee example, I showed you how to use the table to get the p-value. On this one, I'm just going to strictly use the calculator to get the p-value. It's always important to make a picture. Remember to always show your mean. I like to show the t-values as well. There's my sample mean. I'm just going to use 308 and my sample t-score there. And let's go ahead and run this hypothesis test. So stat test. It is a t-test. We're going to use stats. Actually, the x bar and the standard deviation are from my new one variable stats run. My null mean is from the last problem I did, so be sure and pay attention to that. The hypothesized mean here is 300, so I'll replace that. And on this one, we are looking for the values to be greater than the 300 minutes. So we'll calculate this. So there's my t-score, 0.909 right there. P-value, 0.191. And we have most of what goes with this picture. Now the alpha value of 0.025, if you wanted to know what t-score that went with, you could use your inverse t. Remember I showed you that a couple days ago. You could do second distribution inverse t. Put in this area. The area to the left of this would be 0.975. Degrees of freedom here are 11. And this t-score would be 2.201. It's not, you don't have to have that value, but sometimes it's nice to see, especially when you're drawing this, where is your significance level compared to where is your sample. So my sample landed here. The rejection region is here, so we're not going to reject this thing. Let's continue on to the next page. Okay. So if we are using the p-value from the table, if you remember how to do that, you're going to use degrees of freedom of 11, and you're going to look for 0.909 on here. So degrees of freedom of 11, 0.909 in between these two values. So our probability, our tail probability is going to be in between 0.15 and 0.20. So 0.15 and 0.20. Technically, you don't need the exact value that we got from TCDF or our hypothesis test, because this p-value is so big, so much bigger than the 0.025, we know we're going to fail to reject anyway. So we use the t-test. You could use TCDF. I'll go ahead and show you that one again. So it's second distribution, TCDF number 6. And on this one we want an upper end, so our lower boundaries are 0.909. Upper boundary, let's just put in 100, you can put in 1,000. Degrees of freedom is 11. Paste that function. There it is, our 0.191. So you have a lot of choices. Alright, let's talk about our conclusions. Since the p-value is high, and you should really state the p-value here, since the p-value of 0.191 is high, I fail to reject the null hypothesis. Although the sample mean exceeded 300, the difference of 8 minutes, 308, is not statistically significant. I would need more evidence to state the new process improves the battery life. remember here we were trying to show that the battery life is bigger than 300. This sample was 308, great, but it's not that unusual of a sample. Remember, the burden of proof is very high, right? We need to be able to show that the mean battery life is greater than 300. We need an extreme example, and we don't have that. Maybe this 308 is just due to sampling variation. And that's what the next sentence says. The difference of 8 minutes of battery life increase would occur in 19 out of 100 trials, simply due to chance alone. So that's without regard to the new process. All right, let's confirm this with the confidence interval. We do a one sample t interval, two-sided. So the critical t score that corresponds to a 0.025 level of significance for a one-tail is going to be, we're going to double that, so it's 5% on a two-tail, or 0.025 on each side, 95% in the middle. So we're going to use a 95% confidence level. If you are going to work all this out, remember your T star has to reflect not 0.025 but 0.05 confidence level at 11 degrees of freedom would give you a t-score of 1.796. We're going to do it on the calculator though. So we're going to do, it's test number 8, the t interval. We're going to use the stats that are already in our calculator. Confidence level 95%. Be sure and always check that. Otherwise it's just going to have what you used last, which may not be what you want. And our confidence interval here, 288.75 to 327.08. Okay. And what we would say about this, why it supports our answer, is that the value of 300 minutes is included in this confidence interval. Okay, I'm 95% confident that the mean lifespan for all batteries manufactured with the new process will be between 288 and some change and 327 minutes. Because the interval contains 300 minutes, it supports our failure to reject the null hypothesis. When you're doing this on your calculator, finding this confidence interval, you don't actually get to see the margin of error. So if you have a question that asks you about the margin of error, you can always calculate it once you know this. Think about it. This, the y bar is exactly in the middle of this. The margin of error is basically half of this distance. So if you take the larger value minus the smaller value, divide by 2, that gives you your margin of error. In this case, it was 19.16 minutes. All right, we have one more piece to do here, and that is, actually this goes back to the cup of coffee problem, so this is in the wrong set, but I will go ahead and do it because it talks about finding sample size. So in our coffee problem, we had 0.0768 ounces. If we wanted to do another trial to be 90% confident of estimating the mean within some number of ounces, then you would have to back solve this for n, which we did this a couple of days ago in the states problem, I think, or one of the example problems on that page. Basically plug in all your values. Remember, this is all from the coffee, sorry about that, and we would get 73.7. So the sample size to get this margin of error would have to be 74 cups of coffee. You always want to round up. Okay, thanks for watching. Have a great day.